Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 322, coin change. And this is going to be one of the more important dynamic programming problems. It's not a hard one, but you need to know the concepts for this problem. I think it's called the unbounded knapsack problem, where you have an unlimited number of like something you can use, and then you try to hit a total, and you're either going for like the minimum or maximum coins usually. And so in this case, you're given an array of coins and you're trying to hit an amount with the minimum amount of coins. So you're trying to hit the amount exactly, and you want to figure out what's the minimum amount of coins you can use to get that amount. And so for this example, if you're trying to get 11, obviously when you have a 5, 5, and a 1 for a 3, and you only have a 2 coin, you can't do it. And then for a 1 and amount 0, you would have 0 coins. So what we're going to do actually is we're going to draw out the decision tree here, and then we're going to figure out like what's the brute force solution and how we can simplify it, and then we're going to code up the top down and bottom up solution, because this isn't a super long problem, but the concepts are really important to know. So I'll go over them in detail for this one. Okay, so let's say we have coins 1, 2, 5, and we are trying to get the total 11. So what we're going to do actually is we are going to start with 11, and then we're just going to try to use our coins, and then our end state is going to be when we're at 0. So at every state, the brute force would be just try to use every coin in our array and see if we went overboard, right? So we would go use 1. Let's just actually, let's draw this over here. Give us some more space. Okay, so here, let's use 1 coin. So that would give us 10. Let's use 2. That would give us 9. And 5. That would give us 6. Okay, so let's actually finish out the 6 first. That'll be the easiest because it's the smallest number. So we're not going to finish all the way down, but we are going to do a decent amount until you get the kind of the concepts. So obviously one thing we can do is we can keep using 1 coin until we get to 0. So we would just get to do this. This would be like 5, 4, 3, 2, 1, 0. So that's one solution, right? And so another way would be we would use the 2. So we get to 4, we'd use a 5, we get to 1. This get to 1. And then this here, we can only use a 1, so we'd be at 0 here. Okay. And now, let's just finish a little bit more of these, and then it'll be good. So we used a 1 here, so let's try to use a 2. We're at 3. Let's use a 4. We're at 1. Okay, well, this 1 would get only to 0. This 3, we can only use a 1 or a 2, so we can just do like this, right? We can use the 1 all the way down, so 1, 0. Now let's try to use a 2. We'll be at 1. That goes to 0. This 2, we can either, so we can go to 0 if we use a 2. And then this 4, we can use a 1 or a 2. So this 4 would go to 3, 2. It's a little messy. Let's actually not go anymore. So you can kind of see the point of how this would go. Like all of these would just go down until you hit zeros everywhere. Or technically, let's say you did get to a case where you were at like a 2. So what we could do, and what we are going to do is when we code is when we try a coin that's too big, we'll get like a -5, or we'll try a 5, then we'll get a negative number, and then we'll know that's an invalid index. But the thing that we end up doing in all these is, if I draw out this whole thing, especially too, we get the same number a ton of times, right? Like as you can see, even here, you get the number 2 a lot, right? So you get the number 2 a lot. You get it here and here. You get the number 3 here and here. You get the number 4 here, here. And then obviously if you did some stuff over here, you'd get those a bunch of times. And so you're doing a ton of repeated work. So when you draw these decision trees and you see a bunch of spots that you do a lot of repeated work, ask yourself, does it matter how I got to this state? Like once you get to a 4, does it matter how I got to it? Is that going to change how many coins I need to get 4, like a total of 4? Well, not really, right? Like we're not doing some kind of path. We can just add some previous thing to whatever this returns, and we can keep doing that. And so if that's the case, then you're going to want to recognize that you're going to want to use memoization. And so what we're going to actually do is we're going to memoize, and then we're going to have a visited array or visited hash set, and then we're not going to do repeated work. So the most possible DPs we'd have to do here would be 11, right? Because this is a total of 11. So that's going to save our work a ton. Okay. And so now that we know that, let's code up the memoization solution. And then from there, we're going to figure out how we can code the bottom up. And so memoization, I have a ton of problems doing memoization. I usually prefer it. It's easier to code than bottom up. So let's think about it. So first we need a visited hash set. So that's going to be a dictionary, right? Actually, we don't even need a default dict, I don't think. Okay, now we need our standard memoization DP. So as usual, you're going to have, what do we care about in this? So we care about the amount, right? So let's just call that total. Okay, so we only have one thing for the state. That's just the total we're trying to get to. And so our base case, remember, if total is less than. So what we want to do is we want to get the minimum amount of coins. So instead of checking if our coin is valid, we could do that. Actually, do we want to do that? How many coins do we have? So there's only 12 coins, and coins have big amounts. Yeah, I don't think I'm gonna do that. I think I'm just gonna do that. Yeah, like I think I'll just do that in here. So if total is less than 0, that means we have an invalid solution. And so if we're trying to minimize the amount of coins, we can just return infinity here, and that's going to guarantee that we can never minimize that solution, right? Okay. So let's do that. Now, if total equals 0, so in this state, if total equals 0, it means we use 0 coins in this particular state. So we're going to return 0. So that's going to be our two base cases. Is if we're out of bounds, we're going to return infinity, meaning we can't minimize something that's infinity, so we're going to have the biggest number possible. And if it's 0, we want to return 0. Okay. Now our other case is if total and visited, then we could return that, right? We can return visited total. Okay. So now we actually want to calculate the total. And how do we calculate the total? Well, remember, for whatever the total we have, we're just going to go through every single one of these coins and try it, and then we're going to take the minimum. So let's just remember, if we want to take the minimum, we're going to initialize res to infinity, right? And so for coin in coins, res equals min res, or so what's this right gonna look like? Well, it's actually gonna look like 1 plus, right? So when we use a coin, that's gonna be a 1 here. We did use 1 coin, and then dp of whatever the amount is left after we use the coin, right? So amount minus coin. That's gonna be the remainder we have left. So it's actually not gonna be amount, it's gonna be the total here. So that's gonna minimize our res. Now we have to store that in our visited. So visited total equals res, return res. Okay, so that's going to be the DP array. Now, what we need to do is we can't just return this DP total, because if, let's say, all our states are invalid, like for this number 2, then we should get infinity, and so we need to actually return the total if the total isn't infinity. But if it is infinity, then we need to return -1, because right, if you can't get anything, then return -1. And so we can do that in one line. So we can just say return DP. Actually, we don't want to do that, because then we'd have to call it twice. So let's just say res here. DP total return res. Or what we could actually do is we could do, here. No, this is fine. Return res if res does not equal infinity. Else we return -1. That should be it, I think. This is amount. Okay. Okay, so that's the memoization solution. So let's think of the time and space complexity, and then we can think about how we would get the bottom up here. So time, remember we're only visiting each state one time, right? So we do have to recurse down. And what's the most that can be? I think the most that can be is, the most states that can be is, if we're only visiting each state one time and we have amount states, I think this is just time amount, because worst case scenario, our coin amount is 1 and we just keep doing 1, in which case it would look like this, right? It would be the biggest recursion stack would be like 11, 10, 9, and so on if our coin is 1, but that recursion stack would still be amount. So that's, I think that's our time. I think it's linear time here. Well, actually, wait, no, there's one other thing. So what's the length of coins? Actually, I think the length of coins is only 12. Yeah, so the length of coins here is pretty much constant. So at every state, it's going to take 12 times, and there's amount state. So if it's 12 times amount, I think it's just amount. If it was some bigger thing, then it would be bigger. But because coins is only 12, that's just linear. Okay, and then space is O amount as well, because we're storing every number up to amount pretty much in our visited. Okay. So now let's think of the bottom up solution, and what you want to do with the bottom up solution is you want to look at what's your base case, and then you want your first element in the bottom up solution to be the base case. And so our base case here is total so when total equals 0, we're at 0. So let's just do that. So we're going to have an array. So let's have an array, and we're going to have that array from amount to 0. So the numbers here are going to be like, we want an array from amount to 0, and then we want to have some values. So the index technically here is going to be like, we're going to want to have how many numbers, right? So if we have 11, we're going to want to have 12 slots. So let's just do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 slots. And so this last index is going to be 4. So these, I'm not gonna draw the indices here, but I'm gonna draw what the amount should be in this index. So the amount in this index should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and remember the amount of coins we need to get 0 is 0. So then we just look what are we doing in our memoization, and then we kind of want to try to mimic that in our bottom up. So in our memoization, we are looping through the coins, and we are just trying to get the minimal output here. And so we can do the same thing. So we can just in like 1, like let's say our coins is 1, what was it? It was 1, 2, 5, right? So always in the bottom up, you're going to want to start the base case, and then you're going to want to fill out this array going backwards from the base case. Unless your base case is here, then you're going to want to fill it up the other way, but here it's not. So what we're going to do at every index is we're going to try to add these numbers to the index, and then if we are out of bounds, so let's say we try to add 5. If we're out of bounds, that means this is an invalid solution. And so in that case, we would have infinity, right? But if we're in bounds, like let's say we try to add 1, then we take that value, and we want to minimize that. So we would try to go to 1. We do have a value here, and then remember it's 1 plus whatever value it is, because we use a coin here. And then 2 would be out of bounds, and 5 would be out of bounds. So this would be a 1. Now for 2, we would try 1. Okay, that works. So that would be value 2. Now we would try 2. That works as well, and that would be value 1. So 1 is smaller. And then 5 is out of bounds. So for 3, we would try value 1, which would be 2. Right? We keep adding 1 each time. Then we try value 2, which would be 2 as well, so that's the same. And then 5 is out of bounds. So for 4, we would try value 1. That would be 3. We would try value 2. That would be 2. 2 is smaller. 5 is out of bounds. 5 is not out of bounds, and obviously 1 and 2 are going to be bigger than 5, so we're going to use a 5 here. And we're going to keep doing that. So we're going to keep populating these. We're just going to try every single index in these coins. So we're just going to do whatever index we're at plus the coin, we're going to see, are we in bounds? If we're not in bounds, then the result's going to be infinity. Otherwise, it's going to be a number, and we try to minimize whatever that is. So now we just have to code this up, and that should be pretty straightforward. So let's actually comment out this, and let's code up the bottom up. So just say dp in this case. And so what I'm actually going to do is I'm going to set all these values to be infinity to begin with, because we're going to try to minimize them all. Okay, so okay, and so we have, remember, we have amount plus one of these because we need one for 0 as well, right? In our picture, you could see that we have 12 total indices for 11 numbers, so it's going to be amount plus 1 here. And then dp at the last slot is 0. So now we're going to loop from the last index all the way to the front. Sorry, not the last, second to last. So that's going to be for I in range length dp. So -1 is the last index, so we need -2 here. We're going to loop all the way to the start. Okay, and now remember what we need to do is we need to check every single number. So for coin and coins. And so if I plus coin is in bounds, so that's going to be less than length of coins. So if we're out of bounds, it's going to be infinity, but we already initialized it to infinity. So we can just say if we're in bounds, get that value. Otherwise, we don't care. Okay, so if I plus coin is less than length coins, then we just minimize here. So dpi equals min dpi, or 1 plus dp I plus coin. Okay, and so once we minimize, once we like fill out this whole array, like once we get some numbers, whatever, now what we care about is this value here, because we're trying to get the actual total amount. And so it's the same thing here. If it's infinity, that means we don't have a solution, and if it's non-infinity, we can return it. So return dp0. dp0 is not equal, else -1. Okay. Interesting. Let me see what I did wrong here. Should be correct, but let me just double check. So float inf amount plus 1, that's fine. dp -1 is 0, that's fine. In range length dp -2, that's fine. If I plus coin, oh, this is not length coins, this is length amount, right? Yeah. Oh no, sorry, not length amount, it's length dp. Okay. Tough day. Yeah, hopefully that's right. Yeah, there we go. Cool. All right. And so we can do the time and space again here. So time, for every single index, we are going through coins, but we're only at each index once. And remember, since coins is 12, that's going to be big O of n, where n is length of dp. And space, we have a dp array of space amount. So it's the same. So this is, yeah, this is amount as well, technically. So it's going to be the same time and space. I do think sometimes when you have a bottom up, it's a better solution than a top down in terms of space, but in this case, it's the most basic one, so they're the same. So hopefully you get this one, and definitely I would say you're going to want to make sure to know this one. Even if you do want to practice bottom up, this one and like house robber and some easy ones are good to practice, one-dimensional bottom up, because if you can't do one-dimensional bottom up, you're not going to be able to do two-dimensional bottom up, so this is definitely a good place to start. And so the way I would usually recommend doing bottom up is, yeah, do the memoization, understand the memoization, and then the bottom up's not too hard. It's just the memoization backwards, pretty much. Okay, so hopefully you enjoyed this problem, and if you did, please like and subscribe to the video, and I'll see you in the next one. Thanks for watching.